seen Jiang from JA Solar, who will speak about peripheral and edge recombination losses of heterojunction cells. As I mentioned in the beginning, so probably this is the first time, at least for me, JA Solar speaking about heterojunction. A couple of words about Seen. He is a cell technical director at JA Solar. He has a long experience not only in PV, but also with JA. He joined JA's R&D Center in 2008 and has shouldered several responsibilities of development of PERC, bifacial PERC, and N-type high efficiency cells. So, Jiang, please take the virtual conference room.
Can you hear me? Yeah.
Yes.
Thanks for your introduction and thanks for the invitation from the organizer. Now I'm sharing my screen. Can you see my screen?
Yes.
Okay. Okay, the topic of my presentation is peripheral and edge recombination loss of HJT cells. At the beginning, we will talk about the challenges of HJT cells, including the cell cost comparison and the market information sharing. At the second part, we will discuss peripheral and edge losses associated with HJT cells. Then we will probe into the laser cutting loss and compare it with the peripheral loss. Finally, we will give a conclusion. P-type monosilicon PERC continues to be the dominant workhorse for PV industry, as cell production capacity has reached over 300 gigawatt in the past 5 years, while larger sized wafers such as M10, M12 have taken a vast majority of market in the past 2 years, benefiting from lower manufacturing cost and higher power output as demanded by the utility scale power plants. N-type cells with passivated contact on backside has entered the foray, competing with P-type PERC with a very aggressive capacity expansion activity spearheaded by Jinko and Juliward. The traditional high efficiency N-type HJT cells have also seen increased pace of production expansion as the equipment tools for manufacturing the cells are maturing with high throughput for volume production. As the conversion efficiency of mass-produced PERC cell is perceived to have hit the plateau. Nevertheless, its market share is yet to be taken off. One of the hurdles of the expansion of the N-type cell is the cost. Here we provide a cost comparison of 3 major cell structures. 1% efficiency gain of PERT and HJT was assumed. The throughput of cell performance, the throughput of cell production line used in the cost calculation is 6,500, 6,500, and 4,000 wafers per hour for M10, PERT, and HJT cells, respectively. And the N-type wafers for PERT and HJT cells are assumed to be 4% and 2.3% more expensive than P-type wafers, respectively. The calculated cell cost of PERT and HJT are 1 and 3 cents per watt higher than that of PERC, owing to greater capex and the cost of consumptions, mainly from the silver cost. As everyone knows, PERC cell is dominating the market owing to its low manufacturing cost. The annual shipment increase rate of PERC is faster than other cells in the last 4 years. However, this trend will not last. The market share of N-type module is forecasted to increase drastically in 2022. According to GS roadmap, R&D will focus on N-type cells, including HJT, unput with passivated contact, and IBC. Research work of tandem cells has been launched as well. IBC with cell efficiency over 25% and the tandem cell over 27% are expected to be seen. The R&D work of HJT is necessary as this architecture is compatible with copper plating and easier to be integrated with the perovskite cells. Here we talk about the peripheral age losses of HJT cells. To reduce the cost gap with P-type PERC cells, further improvement of HJT cell efficiency is a constant challenge, even with the efficiency of industrial HJT cells being capable of reaching 24 to 25% on mass production lines. One of the hurdles for efficiency further improvement is the peripheral regions, which are intentionally left uncovered by TCO coating for the purpose of edge isolation, as well as the under-passivated wafer edges, causing a negligible efficiency loss. Due to the precision limit of the automated wafer handling systems and the variation in wafer size, the width of uncoated peripheral area normally ranges from 0.5 to 1 millimeter. VOC measured from the area are found to be about 15 milliwatt lower than that in the wafer center. Here is the VOC distribution image of our HJT cell. A common approach to control the peripheral recombination loss is to minimize the width of the peripheral region through PVD tree optimization. Meyerberger reported a 0.1 efficiency gain resulted from 40 milliamp increase in GIC by narrowing the peripheral width in their newly designed PVD trays. Okay, in the next slides, we will probe into the laser cutting induced loss and then compare it with peripheral loss. Yeah. Laser cutting has been widely used in the PV industry for using half cells to make modules. Laser with high pulse energy scribe cells for several times, resulting in 50 to 100 micron wide trench for mechanical breaking. Here is an image, cross-section image after conventional laser cutting. HJT cells are more vulnerable to the heating caused by laser cutting that can degrade the passivation effect provided by amorphous silicon in the so-called heat affecting zone. Thus, conventional laser cutting is not applicable. A less destructive approach proposed by DR laser has been demonstrated to be able to mitigate the navigate effects. Two different kinds of laser were implemented to make a laser guideline and scribe the wafer along the guideline respectively. In this slide, we will compare the less destructive laser cutting loss versus mechanical cleaving. Pure mechanical cleaving leaves clean, smooth, and unpassivated edge along the crystalline cleaving orientation, barely with any damage to the wafers. It serves a good reference to examine the quality of laser cutting. So we have two groups of cells cutted by laser and the mechanical cleaving respectively, and compare the cell performance after the cutting. It can be seen from the RV results that a non-optimized laser cutting caused 0.34% and FF loss and 1 milliwatt VOC loss, comparing to pure mechanical cleaving. This loss can be further reduced by equipment and process optimization. So why we need to compare the loss of the edge cutting and the peripheral recombination loss? Because the influence of edge and peripheral recombination loss depends on wafer size. Wafers with bigger size has relative lower edge to area ratio, will be less affected by the edge effects as well known. However, cells have to be cut into smaller pieces before interconnection for external resistance loss reduction. Laser cutting before cell fabrication to avoid laser-induced damage becomes hot in the industry, as many people believe Gen 2 edge will increase after laser cutting. Comparison of laser cutting induced loss with peripheral loss can be carried out using high definition photoluminescence. Laser cutting induced low VOC zone appears to be smaller than that of peripheral region, as the cell pattern of half cells is symmetrical. Comparing RV characters of the central and edge subcells after laser cutting is a direct measure to judge whether the laser cut edge is more detrimental to cell performance than uncoated peripheral region or not. 4 cells have been cut into 3 or 4 pieces, and the subcell performance will be compared to each other. Since central subcells have 1 more laser cutting edge and 1 less initial edge, if the cell performance of the central subcell is better than that of edge subcell, it means the laser-induced recombination loss is less comparing with the initial edges. You can see the JSC of edge subcells is around 0.2 milliamp per square centimeter, lower than that of central subcells, partially owing to poor passivation of the peripheral regions. Initial peripheral edge-induced FF loss is even greater than that of laser edge in this experiment. As a consequence, the final efficiency of edge subcell is 0.3 to 0.5% lower than that of central subcells. Another way to directly compare the laser cutting induced loss with peripheral edge loss is to remove the peripheral region with laser cutting that replaces the original peripheral edges with laser cut edges as illustrated. Cells from 5 efficiency bins from 22.5% to 24.5% have been used for this test. Laser cutting lines are 7 mm from the original edges. IV curves before and after laser cutting are compared. Efficiency of cells after laser cutting is higher, especially for those initially with low efficiency. Here we can see the IV data before and after laser cutting. You can see GSC increase after cutting, which is consistent with the previous result, indicating PVD uncoated peripheral region bring at least 0.2 milliamp per square centimeter GSC loss. Fear factor remains almost the same after edge cutting. Efficiency increase of high efficiency cells is 0.15%, while this gap extended to 0.80 for cells from lowest efficiency bin, 22.5%. The direct comparison indicates that the loss caused by the uncoated peripheral regions is greater than that of the loss induced by laser cutting. Here is our conclusion. It has been demonstrated that the efficiency loss caused by uncoated peripheral region on HJT cell is greater than that caused by splitting a cell using laser cutting. Our answer to the question that starting with half-size wafers or cutting finished cells into two halves get better cell performance is the latter. Laser cutting induced loss can be further reduced by implementing a new cutting scheme that deploys two laser systems and further process optimization. Okay, thanks for listening. That's all of my presentation. Hi, Sharma.
Okay, thank you. Thank you very much for your presentation.
Yeah.
You know, there might be some questions in the chat room on the technology front, but I would like to take this opportunity since Jay Solar came onto the stage and wanted to speak about heterojunction. So I have one or two questions regarding a very general question. So what is the general plan of Jay Solar's heterojunction pilot line, and you know, how are you trying to increase your scale, and then, you know, what are the wafer sizes you are trying to adopt in your pilot line?
Okay, I answer your question first. Yeah, we have announced that we will establish a pilot line last year, and right now the screen printing machines of 270 megawatt pilot line already arrived last week and has been moved in. PVD and PCVD will be delivered at the end of February. And M10 wafers will be adopted as the default size. Yeah.
So M10, if I hear correctly?
M10, yeah, M10.
Okay, so I think, you know, then we will also save some time if some other speakers might take some time. But, you know, there are already a few questions that are coming in the chat room. So please stay online and answer these questions in the chat function so that, you know, I can move to the next presenter. And thank you very much for your presentation again.
Yeah, thank you, Sarwan. See you.
Okay,